This video is about fundamental trigonometric identities and areas of triangles. As always, read through the textbook and take careful notes, but now consider the following highlights. Let's begin by recalling the fundamental reciprocal identities. We've developed these in previous topics, and hopefully by now they're looking familiar and even working well for you as you practice homework. But let's just recall that cosecant theta is equal to 1 over sine theta. Secant theta is equal to 1 over cosine theta. Cotangent theta is equal to 1 over tangent theta. Tangent theta is equal to sine theta over cosine theta. And cotangent theta is equal to cosine theta over sine theta. And there are some relationships between these, such as reciprocals that we've been working with. For example, cotangent is the reciprocal of tangent. We just want to be familiar with those ratios as we proceed, so make sure that those are being used as you practice. Next, we're going to introduce and understand, hopefully, some fundamental Pythagorean identities. Fundamental Pythagorean identities. Yes, as in the Pythagorean theorem, which you may be familiar with. We've used it already in this course and previous topics. It's a theorem involving right triangles. Now, to get these identities, thankfully there's really only one that we really need to memorize. And what I want to demonstrate is that given that single Pythagorean identity, you can derive or get the other couple forms of it without having to worry about memorizing them as much. So what I mean is this. The most basic Pythagorean identity is simply this: sine squared theta plus cosine squared theta equals 1. Now, this can work with any other variable as well. Sometimes you might see it written with an x instead of a theta. The variable there doesn't really matter as much as the actual equation itself. And when we understand this Pythagorean identity as the foundational one, we can get others directly from it. Here's what I mean. So we'll consider that like the fundamental Pythagorean identity. But then if I take that exact same thing, so I'm just going to demonstrate this. If I copy that exact same thing out, sine squared theta plus cosine squared theta equals 1, and I do a little bit of algebra on that equation, such as what would happen if I divide all the terms on both sides by sine squared theta? Well, let's actually do this and see what happens. So left side and right side, I'm dividing each term by sine squared theta. Now, algebraically, let's simplify what we have and see what results. So sine squared over sine squared theta for the first term would really just be 1, right? The next term would be cosine squared theta over sine squared theta. Well, think about this. If you go back to the fundamental reciprocal identities we already know, cosine squared over sine squared. Okay, so we could actually write this. I'll do some slight algebraic rewriting here. Instead of cosine squared theta over sine squared theta, that's really the same thing as cosine theta over sine theta squared. And so if we think of it that way, really the squared notation, we know from exponent rules that the squared would be applied top and bottom, just from algebra here. So if I wrote cosine squared theta over sine squared theta as really just cosine over sine squared, all squared in parentheses, then really that means I'm looking at the following. It's 1 plus cosine over sine, as we saw previously in our fundamental reciprocal identity. Cosine over sine is really just cotangent, which means this is really just cotangent squared theta. And that equals, on the other side, 1 over sine squared. Well, in the same way, 1 over sine is really cosecant. And so if we simply replace that, we have cosecant squared theta, which is 1 over sine. So what we're seeing is that if you break down the algebra here, and let me highlight this in some colors to make sure it's super clear, then in the middle term we have this cosine squared over sine squared, and that's the same thing as cotangent squared. And then moving on to the other side, we had 1 over sine squared, which is the same thing as cosecant squared. And that's just using the definitions that we had already written out for those trig ratios, or those reciprocal identities as we called them. So with that being the case, this second way of writing the Pythagorean identity is just as useful. All we did was divide everything by sine squared, which means we could probably redo that without having to worry too much about memorizing this other form of a Pythagorean identity, but it's just as useful. So 1 plus cotangent squared equals cosecant squared. Of course, theta being the angle we've used here. All right, well, similarly, instead of dividing everything by sine squared, what if we took the exact same equation, which I just recopied? So the original Pythagorean identity of sine squared theta plus cosine squared theta equals 1. But let's divide everything this time by cosine squared theta. All the way through each term divided by cosine squared theta. What would happen this time? Well, let's take this one term at a time. The first term now is going to be sine squared theta over cosine squared theta. Well, okay, again, given that we know just sine over cosine is the definition of tangent, as we've already discussed, then this is really just, for the same reason we already did, this is really just tangent squared theta, right? Sine squared over cosine squared would be tangent squared, just like sine over cosine is tangent, and then we're squaring it, like we demonstrated in the previous one. So with that being the case, we can write that first term as tangent squared theta. This time the second term is cosine squared theta over cosine squared theta, which of course is 1. So now we're looking at tangent squared plus 1 so far is equal to, on the opposite side, now we have 1 over cosine squared theta. Now, can you look back and guess where this is going? What is 1 over cosine? Oh, right, it's secant. So really this is, since it's cosine squared, 1 over cosine squared is the same thing as 1 squared over cosine squared. We won't write it that way every time, but the point is 1 over cosine is really secant, but since it's squared, we're looking at secant squared. All right, so for that same kind of reason, if you just simplify after dividing all the terms by cosine squared theta, we get another Pythagorean identity, which is tangent squared plus 1 equals secant squared. Of course, theta being our angle input here. Now, these should be committed to, I will say, memory, but really, as you can tell, if you just memorize the first one, then without too much trouble, you're just dividing by sine squared or cosine squared, you can get the other two forms of these Pythagorean identities. They're all equally useful, and we'll be using them as needed, and you'll see examples of this coming. But for now, I just want to demonstrate that maybe rote memorization is your preference. You can do that for these, or you can memorize the first one and without too much trouble get the second two. Okay, and then next let's move on to this very same topic to the area of a triangle. Now, you may be thinking, wait a minute, area of a triangle, I already know how to find the area of a triangle. It's 1/2 base times height. We've been doing that in algebra class for years. Okay, that's probably true. However, what we're going to do now is use a trigonometric definition or formula for the area of a triangle. And specifically, here it is. So the area, which we'll just use a capital A for area. I think some textbooks use like a fancy scripted A. It's just a fancier capital A, but we'll use capital A. The area of a triangle with sides of length A and B. All right, so we're looking at side lengths and with included angle theta is as follows. Now I'll explain included in a second. All that means is that if you have, here's our formula, A for area is going to equal 1/2 AB sine theta. All right, so this is our formula. Now, what does included mean? Well, all it means is this. If you have a triangle with sides A and B, obviously you would have side C as the other side, which notice is not part of this formula, so we're just going to ignore it for a second. But the point is this: if you have sides A and B, then the included angle is the angle made by those two sides where they come together. So this could be, spun around or flipped around and oriented in various different directions. But the point is you have a side A, side B, and maybe you're given actual measures for those. And where those two meet at the vertex, we're calling that the included angle theta. So that's all that means. And with that formula, we can find the area of that triangle given that information. Okay, well, let's spend a little bit of time going through some examples that will use some of these ideas here. Our first example says this: write the first trigonometric function in terms of the second for theta in the given quadrant. All right, and then we're given more information. So we'll do a couple of these. The first one being this: they give us cosine theta and then sine theta, and the order matters because of the instructions here. It said write the first trigonometric function in terms of the second for theta. So we have to know which one's first and second. We're just kind of going left to right here in the order they're given. So cosine is the first, sine is the second for this first example, and then it says theta in quadrant 4. All right, so let's think about why that might matter. And first of all, we want to identify, is there a way that cosine and sine can be put together in the same equation? And hint, we're using one of the Pythagorean identities that we've listed above already. So we'll go back and recall, we have a few of those we can use. And yes, sine and cosine both exist in one of them. We'll use the most basic one. So I'm just going to copy this down. Sine squared theta plus cosine squared theta would equal 1. That's the most fundamental Pythagorean identity. Of course, you can switch the order for sine and cosine on this. Addition is commutative, so you could have written it as cosine squared theta plus sine squared theta equals 1, same thing. All right, so the question is, can we write the first trigonometric function in terms of the second? Well, the first one that was given in this problem was cosine theta. So what this means is, can we solve for cosine theta? Can we get that by itself and then end up with sine thetas maybe on the other side of the equation? Well, I think so. Let's do a little bit of algebra. To get cosine squared theta alone first, let's simply subtract sine squared theta from both sides, just using equation solving skills here. If we subtract sine squared theta from both sides, then of course they're gone on the left side, the way I've written this, and the only thing over there would be a cosine squared theta, and it would be equal to now what's on the right side, which was the 1 that was already there, but now minus sine squared theta, because that's what we subtracted from both sides. Okay, so we're getting there. What we'd like to do is be able to get the cosine by itself, not just cosine squared. And so we can do a little bit more algebra to accomplish that. Let's now just take the square root of both sides of this equation where it is. We know from algebra that we can do this with being careful. That would leave us with a cosine theta on the left side because we're taking the square root of cosine squared, which would cancel. However, they would cancel at the cost of putting a plus or minus on the opposite side. So this, as you may recall from algebra, is necessary. If you're taking the square root of both sides of an equation, you have to put a plus or minus on one of the sides because of some of the details that happen when square rooting both sides of an equation. We can just summarize it with a plus or minus, which means we have now cosine theta equals plus or minus square root of 1 minus sine squared theta. Okay, so importantly, remember, you cannot cancel the squared that's with the sine underneath this root. So it's not the case that when you take the square root of this 1 minus sine squared, that the square root there and the sine squared would cancel. That's not the case. You may recall some algebra rules on that. So we have to leave it as is underneath the root, 1 minus sine squared theta. Now, notice we have plus or minus, and we haven't used all the information yet. So if we back up a second and recall that they told us that theta is in quadrant 4, that was part of this problem, then let's recall our quadrants to know what that means, right? If you're looking at quadrants, and in this case, we're looking for cosine theta, which is the one we're solving or getting by itself, right? In quadrant 4, which is in the lower right region. This is Q4 in the bottom right corner. In that region, cosine of theta, or cosine of x, cosine of any sort, is positive because, remember, cosine refers to the x-coordinates of something on our unit circle, you could say. And to the right of the y-axis, cosine is positive. Therefore, in quadrant 4, cosine is positive. So what that means, since cosine is positive in quadrant 4, we're really only using the positive version in our plus or minus. So what that means is we're going to ignore the negative one and simply write our answer as cosine theta equals, and then you could just not write anything. It's really the positive one we're looking for, so you could write a plus sign if you want, but remember, a plus sign doesn't have to be written. You could assume that with an invisible sign symbol here that it's actually positive. So we'll say cosine equals positive square root of 1 minus sine squared theta. All right, let's do a similar thing with example B, still really within the same instructions here, but the next one says secant theta first, then tangent theta second, and then theta in quadrant 2. All right, so kind of like we've just been doing, we're going to write the first function, that's secant, in terms of the second, that's tangent. So all we got to do is remember what the Pythagorean identity is that involves those two trig functions. So you can scroll back, or maybe you've already been working with this a little bit by now. You might remember that we have one involving a secant and a tangent. It's that third Pythagorean identity we got, and of course we got it just by dividing the original one by cosine all the way down. What it ends up saying is that secant squared is 1 plus tangent squared. So we'll go ahead and bring that into play here and recall secant squared theta equals 1 plus tangent squared theta. Now notice I rewrote that in the opposite order. The way I had written it above was with the secant squared on the right side and the 1 plus tangent on the left side. The order of an equation doesn't matter. You can flip it back and forth, left and right. It's still an equation. Therefore, I wrote it in this way as secant squared on the left side equals 1 plus tangent squared on the right side. The point is, we're trying to solve the first expression in terms of the second, which means I want to get secant of theta alone. Well, like we did just previously, you may recall, we'll simply take the square root of both sides at this point in order to undo the squaring that is currently over that secant, which means, of course, we now just have secant theta equals, and then, yes, plus or minus, until we know further here, plus or minus, when you take the square root of both sides, the square root of 1 plus tangent squared theta. All right, so now which is it, the plus or the minus? Well, now we're in quadrant 2, so let's recall what that means for us. In quadrant 2, which is the upper left region of our coordinate plane, we're trying to figure out what the sign of secant is here, right? Because we're solving for secant, so secant theta equals a plus or a minus. Well, which one is it? Remember, secant is really what? Well, if you go back up and recall with the ratios, secant is 1 over cosine. So if that's the case, we're really concerned with cosine's sign. That is the SIGN sign. You'll get used to this quickly. That sign has a couple different meanings. SINE is in our trig function, and SIGN as in the plus or minus, positive or negativeness of something. So in this case, we're looking for secant. Secant is 1 over cosine, which means I'm really concerned with the sign of cosine, because that's the same thing as the sign of secant, the SIGN sign. Well, in quadrant 2, since cosine is negative, because cosine is the x-coordinate of our coordinates along the unit circle, in quadrant 2, cosine's negative, therefore secant is also negative, which means for us, we're working with the negative version of our plus or minus in quadrant 2, which is what we were told theta is in. Okay, so there it is. So secant, which is 1 over cosine, cosine's negative, therefore secant's negative in quadrant 2, which means we can say for our final result that secant theta is equal to negative square root of 1 plus tangent squared theta. All right, let's try a couple other examples. Now we're getting a new set of instructions. It says find the values of the trigonometric functions of theta from the given information. All right, so notice it doesn't say which trigonometric functions, which means we're going to assume it's all of them, all 6 functions. We have 2 examples within this. Part A says this: tangent theta equals negative 3/4, comma, cosine theta is greater than 0, in other words, positive. All right, so let's think through carefully what this could mean. So we know the trig ratios for sine, cosine, tangent, secant, cosecant, all those things above, cotangent, and we're going to leverage or use that to our advantage. Notice here a couple things. Tangent theta as given is negative. We're going to highlight this because this will come out helpful for us. So tangent theta being negative, and yet cosine theta being positive. So let's think through, in terms of our quadrants, I think a picture actually is pretty helpful on this one. So think about where tangent is positive or negative. Since we know tangent theta equals sine theta over cosine theta as defined in our trig ratios, then we want where tangent is negative, that would be the case where sine or cosine is negative, but not both. So tangent being negative, that would occur in quadrant 2 or quadrant 4. Right? So let's just kind of note that's the case there. In fact, I'm going to highlight this accordingly so that it's hopefully easy to follow. So tangent theta being negative, that would only happen in quadrant 2 or quadrant 4. But then let's see with another, I'll highlight with something different here. Where would cosine theta be positive? Well, that would be in quadrant, let's see if you can name it, cosine, that's x value. Where is that positive? Well, that's going to be quadrant 1 or quadrant 4. So we'll note that's quadrant 1 or also quadrant 4. So notice there is a quadrant where both of these are true. It's quadrant 4. That's where tangent can be negative and where cosine can be positive. If you still feel like you're a little rusty on the whole positive negativeness of quadrants and trig functions, don't panic, just keep reviewing it. Go back and review. It goes really all the way back to the unit circle that we started everything on with x's and y's and quadrants and things. So we're really just building on all that stuff. Hopefully it's getting familiar. If not, don't panic, just review it or ask questions, certainly. So we know tangent is negative 3/4 because it's negative. That means it's in quadrant 2 or 4, which I've highlighted in yellow. And we know that cosine of theta is positive, which only happens in quadrant 1 or 4, which I've highlighted in green. Well, if both of those have to be true, then where are they both true? Well, it's got to be quadrant 4. So that tells us where we're working, and that can be helpful. There's a couple ways to do these kinds of problems, and one of them is more algebraic, just relying on the rote formulas that we've used above, like for Pythagorean theorem and all the identities, or sometimes visually is also helpful, which is what I'm demonstrating here. And that is, you know exactly now you're stuck in quadrant 4. What we can do is put theta in that quadrant. So we can just draw a central angle, meaning an angle that has that touches the center of our coordinate system, and we can make a right triangle going back up to the x-axis, just for reference here, and put theta in that central angle position. So we have a triangle drawn, a right triangle drawn in quadrant 4 with central angle theta that is kind of squeezed between the radius of our triangle, the hypotenuse of it that's sticking out, and the x-axis, the positive x-axis. If we know that tangent of theta is opposite over adjacent, which we know, and we know that tangent is negative 3/4 as given, we can label the following without a doubt. We know that the vertical side of this triangle must be -3, and the horizontal side must be +4. Now, why would that be the case? Well, think about it. Tangent of theta is opposite over adjacent, so that would be like -3 for the opposite over the adjacent being 4. That's the positive x side of our triangle leg. And we can therefore fit this ratio exactly to that, and we know we're in the right quadrant because that's where tangent would be negative. Sometimes there's a question like, well, how do you know where the negative sign goes? Does it go with the 4 or the 3? Because a fraction of each of those could work either way if it's ultimately negative. True, however, putting this all together with opposite and adjacent, think of it opposite being a negative downward side from the x-axis, therefore a -3 would make sense vertically there. And then if we're in quadrant 4, then the x component or coordinate to get over to the right on this leg would be a +4. That makes sense as well in a positive direction. Furthermore, cosine has to be positive, which means we know we're in the right zone there. So with those sides labeled, what we want to do is find all trigonometric ratios. Now think about this. We have tangent already, so we can get, well, many from there. So if you want to go directly from tangent to cotangent, remember, they're reciprocals. So if tangent is -3/4, guess what? Cotangent would be -4/3. So that just comes directly from what's given. And the order in which you find these is not really that important. You can kind of make your way through any way you'd like. We could find sine and cosine pretty easily as well. So let's do that. So sine theta. And once you have the picture drawn, it's pretty easy to get the rest of these. You can just use all the trigonometric ratios we know, such as SOHCAHTOA, right? So sine is opposite over hypotenuse. Now, the one thing we don't know yet is the hypotenuse, but we could find it pretty easily because we know that r square, as we did back when we introduced the SOHCAHTOA, we know a formula for r. We could say r is equal to the square root of, in this case, 4 squared plus -3 squared. That's like just using the Pythagorean theorem for this triangle, like a squared plus b squared equals c squared, that thing where r is the hypotenuse that we're looking for, and then the a and the b are the 4 and the -3. The negative becomes insignificant because you're squaring it anyway, as we did here, so we have -3 in parentheses squared. So if we just do a little bit of simplification here, we can say that r is really the square root of 4 squared is 16, -3 in parentheses squared is 9, 16 plus 9 is 25, and the square root of 25 is 5. We'll just write that there. So r must be 5. With that being the case, now we have everything we need. We can find all of the other trig ratios. So I'm going to label this here in our diagram, r equals 5. So that means sine is opposite over hypotenuse, which for where theta is would be -3 over 5. And you can put the negative with the 3, which we kind of already had it labeled that way, or you could put the negative out in front of the fraction. It really doesn't matter because the negative in the numerator is the same thing as a negative in front. So either way is okay on that. So there's sine is -3/5. We could easily find cosine theta. Cosine is adjacent over hypotenuse. Well, again, given the drawing of our triangle here, adjacent would be 4, and hypotenuse we just found is 5. Therefore, cosine theta would be 4/5. It's positive. Notice it's positive in quadrant 4. Cosine is positive. That's good. So we have sine, cosine, tangent we were given, cotangent we found from the reciprocal of tangent. Let's see, next we could do secant and cosecant. So secant, remember, secant is 1 over cosine, which means we just flip over cosine. It was 4/5, now it's going to be 5/4 for secant, the reciprocal of cosine. And lastly, cosecant theta. Cosecant is 1 over sine, the reciprocal of sine. Well, sine of theta was -3/5, so cosecant would be -5/3. A reciprocal is still negative, and so we'll keep it that way. Cosecant theta, -5/3. All right, let's move on to example B. Still in the same instructions here, we're trying to find all the trig functions for the following given information. First, now we're told that cosecant of theta equals 2, and we're told that theta is in quadrant 1. All right, so let's put this together to see what we can learn. So remember, a cosecant, as defined above or previously, cosecant is 1 over sine theta. So cosecant theta is 1 over sine theta. We're given that that's equal to 2. Well, okay, fine. So 1 over sine theta equals 2. We'd rather have something more useful like just sine theta, not 1 over sine theta. So you could flip both sides of this equation upside down. This would be, some algebraic work. Just using proportions, you can flip them both upside down, which would give you sine theta instead of 1 over sine theta equals, and then instead of 2, it would be 1 over 2. So you're just kind of flipping both sides of the equation upside down, which is totally valid to do in a proportion like this, algebraically. What that gives us is sine theta equals 1/2. Well, okay, there's one of the things we already need anyway. And we were given cosecant theta, which is another one we already need. So we're well on our way. Now, we're also told that theta is in quadrant 1. So let's pull out a little diagram to make sure we're working with everything correctly here. I'm going to draw a diagram with quadrant 1, which is the upper right region. I'm going to draw a central angle there, kind of like we did before, with a right triangle going down to the x-axis so that we can use all of our Pythagorean stuff. I'm going to put theta as our central angle, which is now made by the radius or the hypotenuse of our right triangle and the positive x-axis. That's where theta is wedged up there in quadrant 1. And what we know is that sine of theta is 1 over 2, but we also know that sine of theta is opposite over hypotenuse. So opposite of the side for theta would be 1, and the hypotenuse then would be 2. If sine theta is opposite over hypotenuse, and it's also equal to 1 over 2, then opposite could be 1, hypotenuse could be 2. Now, the hypotenuse is always positive for our triangle in our central angle position. It's like a radius of the circle. We've used that before. But then notice if we're in quadrant 1, then the vertical leg of our triangle should be positive as well, which means a positive 1 works there. And actually, since we're in quadrant 1 and we know that cosecant was positive 2, we know then that sine is positive 1/2 because, again, cosecant is 1 over sine. So, with that being the case, we could use the Pythagorean theorem to find the other missing leg of our triangle, right? If you wanted to give that a name, you could. You can call that A or something like that to find the Pythagorean identity, like a squared plus 1 squared. I'll write this out here. So a squared, I'll label the missing side we need as A. And then what we know is a squared plus 1 squared would equal 2 squared. That's just using the Pythagorean theorem for the triangle that we have in quadrant 1. This, of course, would mean if we solve for a squared, we'd have a squared equals 4 minus 1. That is, 2 squared is the 4 on the other side, and then 1 squared is 1. I'm subtracting from both sides. So a squared equals 4 minus 1, which means a squared equals 3, which means a equals the square root of 3. So I can label that missing side as the square root of 3. Of course, it's positive since we're going to the right. We're in quadrant 1. It's working out just fine with a positive x-axis value of square root of 3. All right, if that's what we know, then we can find everything else we need. So we already know cosecant, that was given. Now we know sine, we figured that out quickly. We could easily find cosine. So cosine, given our picture, is adjacent over hypotenuse. Well, adjacent to our theta angle as we've drawn it would be the leg that is square root of 3. So there's adjacent over hypotenuse we already found is 2, or we knew that that was 2. And what we could say then, cosine theta is square root of 3 over 2. And from here, it just kind of starts falling like dominoes. I mean, think of this. If we know sine, then we know cosecant because they're reciprocals, right? So we could say this, cosecant theta, which is 1 over sine, as we've defined it above and previously. Then if we know sine is 1/2, cosecant is the reciprocal, which would be just 2. 2 over 1 or just 2. If we know that cosine theta is root 3 over 2, then, well, secant theta is its reciprocal, which would be 2 over root 3. So I used just the reciprocal of what we knew cosine was for secant. But you will often see this rationalized. We've seen this a little bit already. So I'll just kind of coordinate this here with a different color. To rationalize, you could multiply numerator and denominator by square root of 3, which would give you a more refined version of this, what you'd probably typically see, which is that secant theta is 2 square root of 3 over 3. That's the rationalized version for secant that does not have a root in the denominator. So secant is 2 root 3 over 3. Okay, so what's left? We have sine, cosine, cosecant, and secant. Let's see, we need some tangent and cotangent. Let's get those in play here. So we could say tangent of theta, and we can use the same, once you draw the picture according to the given information, you can just keep reusing it to get all the other ratios that you need. So given where theta is in our diagram and that tangent is opposite over adjacent, the opposite side to theta would be the 1, and the adjacent side right next to it would be the root 3. So tangent would be 1 over root 3. Of course, you would probably see that rationalized as well, which you'd be multiplying top and bottom by root 3, and that would give you root 3 over 3 for tangent in its rationalized form. And then, of course, cotangent. Cotangent is the reciprocal of tangent, which in its most raw form was 1 over root 3, so that's the easiest to flip over. You'll just get root 3 over 1, or just root 3. So cotangent is square root of 3. And one quick way to make sure you've covered all your bases here is that you should end up with 6 different functions. We have 6 trigonometric ratios that we're using, or functions. And so if you can quickly count all 6, you know you've got them. Now keep in mind, we were given one of them, actually in both of these examples, right? That was, like, for example, cosecant theta was given in this problem, so that counts as one of the 6. Just like tangent theta was given in the previous one, that counts as one of the 6. So that give you a quick way just to count up and make sure you've got them all. All right, let's go on to a next example. This one states as follows: a triangle has an area of 16 inches squared, and two of the sides of the triangle have length 5 inches and 7 inches. Find the angle included by these two sides. Okay, so that should be some familiar language from the formula we wrote above. Remember, we said that area is equal to 1/2 AB sine theta, as long as A and B are the sides that have the included angle theta, which means, again, you have sides A and B that meet somewhere for this triangle, making one of the vertices of this triangle, and that's where angle theta is. And we have these two side lengths given as 5 and 7, so we could write them in here just to make sure we're understanding exactly what's happening. That's what the diagram would state. Now, what this question says is the area has, or this triangle has an area of 16 inches squared. So instead of A, we could just write it as 16 because we know that. And then if we just plug in the rest of the formula here, we'll copy down the 1/2. So 16 equals 1/2, just like A equals 1/2. Then it's A times B. Well, they told us those are 5 and 7. It does not matter which one is which. So I'm just plugging those in for A and B. And then we have sine theta at the end. And then the question says find the angle, that's our theta, included by these two sides. So we want to figure out what theta is in this equation now, which states 16 equals 1/2 times 5 times 7 times sine of theta. Okay, so think for a second how we could try to get theta alone. And you might wonder, well, how could we get rid of all these, numerical factors in the front? Good question. Maybe we should do that first and just kind of get sine theta alone and then worry about getting rid of the sine so that theta is by itself. So let's do that. This really means if I were to multiply both sides like by 2, let's see, I'll put this in a different color so we can just do, it's just doing some algebra here. If I multiply both sides by 2, then what we're really working with is 32 equals, those 2's would cancel the 2 and the 1/2. We'd have 32 equals 35, that's 5 times 7, sine of theta. So our goal is to find theta, which means we want to work on getting that alone next. So let's divide by the 35 that's in front of the sine, right? Because at this point we have 32 equals 35 sine of theta. That's just us kind of working on getting sine theta alone first from this original area equation. So next, I think we should divide by 35 on both sides, which is then what would cancel those 35s, and that would give us sine theta all alone. I'm going to copy this down. I might even switch the sides of it, which don't matter as much. So we have sine theta all by itself. It would be on the right side if you're keeping sides here, or you can switch. I'm going to write on the left side now, and that's equal to what's on the other side, which is now 32 divided by 35. Okay, that's fine, but we're trying to find the angle, theta. So the question is, how do I get rid of the sine, right? Well, from what we've already discussed about inverses, we can use them in order to accomplish this. So what I'm going to do is this. I'm going to move down to get a little bit of extra space so you can see this visually. We currently have sine theta equals 32 over 35. I'm going to just kind of rearrange to get some space. What we want to do is take the sine inverse of both sides of our equation. So I'm taking the sine inverse of the left side, which I've now written, or I had written as sine. So it's sine inverse of sine of theta. And that equals the other side, which is sine inverse of 32 35ths, or 32 over 35. Now, the whole point of doing this is that the sine inverse and the sine will cancel each other out, leaving us with, well, just theta on that side of the equation. So what we have is theta equals sine inverse of 32 over 35. Now, we can figure out what that equals thanks to a calculator. So now take out your graphing calculator. Let's actually crunch this. So to turn it on, we have to make sure we're in degree mode. Well, it depends. You could do radian or degree mode. I think typically a textbook would be using degrees for this kind of problem, so we'll do that. You could use either. Remember, you got to check it with the mode, so turn your calculator on, go to mode. I'm using degrees, so that's the third row down, or it says radian or degree. Let's go select degree, and then we'll go back out to our blank screen where we're going to type in exactly what we see for theta. So theta is sine inverse. To do that, you have to hit second and then the sine button, which puts a little sign with a -1. That's the inverse symbol in your screen. So we have sine inverse of, we want 32 divided by 35, which we'll just type in, close the parentheses, hit enter, and turns out there it is. So 66.10449181. And I don't think this problem gave us any rounding instructions, so when in doubt, give it a couple decimal places. We'll call this 66.10 for our results. So we'll go ahead and write that in, and we'll say approximately, that is approximately 66.10, or just 0.1 would be probably acceptable as well. It's really just using the area formula we listed above, but kind of backwards. We're filling in the area that we already knew and then had to work back to get the angle. Okay, let's do one more example. This next one states as follows. It has a diagram with it, and the diagram is, as I will describe, it has a circle with a center point, and extending from that center point to a point on the circle, we have a radius of 2. The central angle then is made with that radius and another radius that is extending upward to a point on the circle. Of course, that radius would also be 2. It's not labeled, but it's not necessary to label it. Every radius is equal. So let's say we have a radius of 2, and if you put 2 of these radii together meeting at the center of the circle, then the angle formed by these radii is marked as 120 degrees. And then where those 2 radii meet the circle at their respective points, you could connect those points with a lined segment from one of the places the radius hits the circle to the other. And that segment is drawn but not labeled. In this problem, it says, find the area of the shaded region. Now, what's not drawn that I'm going to draw for you is that the shaded region is really the portion that would be outside of the triangle, between the triangle and the circle, so that it's not a full semicircle, but it's kind of like a partial of a semicircle, you could say. So the segment connecting the points where the radii hit, if you were to imagine the space between that segment and the outer edge of the circle, that's what we're talking about for shaded region in this problem. Now, really our only chance of finding such an odd shape of a region, it's not a sector, it's not even a semicircle, it's like a chopped off piece of a circle, you could say. So our best bet to do that would be to find first the area of the entire sector made by these two radii. So if we kind of just trace that out, each radii goes from the center of the circle to the outside, of course. We've already kind of described that. And if you can picture the sector made when you connect or cut out, if it were like cutting out a piece of a pie, it'd be a large piece. That's a 120-degree piece of the pie, which is actually a third of the whole pie, right? So if you imagine that entire sector, we could find the area of that because we've already discussed areas of sectors. And then if we simply subtracted the area of the triangle that we also described, which is inside the sector, then if you subtract the area of the triangle from the sector, that leaves, well, the exact piece we're trying to find. So that's our game plan, all right? So let's just kind of do that one piece at a time. I'm going to say it this way here. Let's recall the area of a sector. This is from a previous topic. We said that was A equals 1/2 r squared theta. So that's just kind of bringing back something we reviewed a few topics ago, or did a few topics ago. Area of a sector is 1/2 r squared theta. Why is that helpful? Well, because that's exactly what we're looking at for this large piece of our pie, this 120-degree piece of our pie we're cutting out here. We want that full sector area. So that would be 1/2 times the radius squared. Well, the radius is given as 2, so that's 2 squared. And then times theta, which is given as the 120 degrees. Okay, so let's crunch this out first. This area would be 1/2 times 2 squared is 4. So really 4 over 2 is 2 times 120, which would be 240. But importantly, this is in degrees, right? So let's keep track. This was given as 120 degrees. That was how the diagram was labeled. We're using that 120 as our theta for our formula for the area of a sector, which means we're looking at 2 times 120 degrees, which is really 240 degrees. Well, that's fine, except it doesn't make as much sense. When we're doing actual geometric measures, radians are what we need because they're actual lengths or measures. So what we're going to do is convert 240 degrees into radians. Remember how to do this? This is also a previous topic. To convert from degrees to radians, we multiply by a ratio. Remember, the degrees have to be on opposite levels to cancel. So the 180 degrees is below it, and the pi is above it. So if we multiply 240 by pi over 180, and then simply reduce, that is, you're reducing 240 divided by 180, just as a fraction, and that should give us 4/3. And then, of course, pi has to be along for the ride as well. What I mean by the reducing, you can do this on a calculator. You're trying to calculate 240 over 180, but then in reduced form. So we can just do this by plugging in 240. This is in a TI-84 Plus graphing calculator. 240 divided by 180. If I hit enter, it'll give me a decimal approximation. We don't want that. We want the reduced fraction of it. So we hit the math button, and then the first option will turn things into a fraction, and it will reduce it in the process. So if I hit enter, it gives us 4/3. So that's where our 4/3 is coming from. And of course, we had to have the pi there as well. So we're looking at 4/3 pi. Now what is that? That's the area of the entire sector. So actually what I'm going to do is color coordinate that appropriately. I've been doing that all in orange, so I will keep that the case. So we have 4/3 pi as the area of the entire sector, as if we were cutting out a third of this entire circle, or pie. If it were a pie like we're eating, right, a third of it. So in that case, that's the first thing we need, but we also now need to find the area of the triangle that we're going to be subtracting from that. So let me kind of shade this. I'm going to use a pink color for this triangle because this would have to be subtracted from the entire sector in order to leave us with just the blue portion I've drawn in blue, which is like the outer side of this sector that's chopped off of the full sector. So let's do that next. We can find the area of the triangle, well, thankfully, using what we just wrote above for our triangle area formula, which is 1/2 AB sine theta. So for us, plugging what we know in, as given in this triangle, it'd be 1/2 times 2 times 2, because you could say like the A and the B are each 2, just the radii of the circle in this case. So that's 1/2 times 2 times 2 times the sine of the 120 degrees as given for that angle measure for theta. And we can, it's given in degrees, we can use it in degrees. We're getting an area measure. This will just be a numeric value. We just got to make sure we're in the right mode of our calculator when we type in the 120. So let's in fact go there next. We pull out our calculator and let's type this in as we see it. So I'll type it in as 1/2. I'm going to put that in parentheses to be super careful with fractions as always. 1/2 times 2 times 2. You could put that in as just times 4 if you wanted to. Just typing it in actually as we wrote it. And then the sine of 120. And I got to make sure I'm in degree mode, so I'll just go quickly check on that. Yep, in degree mode. Okay, so now we'll go ahead and hit enter for this, and it gives us a result of 1.732050808. Now, there's another way to do this kind of problem, which I want to demonstrate also, and that is using exact values. You'll find this is a more precise way. Often textbooks will do this same thing. So if I simplify what we have in our calculation, we just showed the decimal approximation of it. But if I simplify the first part of it, the 1/2 times 2 times 2, like the 1/2 times 2 could cancel, we really have 2 times the sine of 120 degrees. But we could find an exact value for sine of 120 really just using our unit circle knowledge, right? So if you go back to the good old unit circle, remember 120 degrees would be, if you start standard position and rotate counterclockwise, 120 degrees is in quadrant 2. It's like the 2/3 of the way all the way across the first half of circle. So that's the 120 degrees. And you may recall that on the unit circle, if you mark where that would be, those coordinates are ones that we've already worked with pretty extensively. So we could probably leverage what we know. If you think unit circle here, the x-coordinate there would be a -1/2. The y-coordinate would be a positive √3/2. So I'll just kind of note here, recall. Good old unit circle, which has this information on it. We've already been using this. It's just a quick way to recall and get some precise values. In other words, the sine of 120 degrees is the y value at that terminal point, which is, well, square root of 3/2. Then these 2's would cancel since we have 2 times the square root of 3/2, and that would leave us with just the square root of 3. So now, what's the big picture? We're trying to find ultimately, remember the sliced off portion of our sector, which I've colored in blue or shaded in blue, and that's the whole point. Find the area of that shaded region. When I say shaded there, I'm referring to the region shaded in blue that is chopped off as part of the sector. So what we really need is the area of the whole sector. So let's put this together. The area of the blue region is the area of the whole sector, which is the 4/3 pi we already found. I'm just going to copy that. from where we got that earlier. Bring that down into our final result here. So it's 4/3 pi, that's the area of the entire sector, minus the area of the pink zone, which is just the triangle that's kind of part of the sector. We just found that to be the square root of 3. So I'm going to bring that, copy that down in place as well. So this final result in exact form is not going to be very pretty. There's no way to combine these terms. This would not be something to simplify. You could leave it in this form as maybe 4 pi over 3 or 4/3 pi minus the square root of 3. That's a valid form of the answer. That's called the exact form. Or you could approximate this on a calculator, which, well, let's do that real quick just to make sure we've got this. If you open up your graphing calculator and then type in the first term, which is 4 pi, you have to use the pi button for this, which is typically above the little caret button. So if I do 4 pi and then divide that by 3, if I hit enter there, it'll give me the result for that first term, which is approximated as 4.188790205. Now, I wouldn't want to round that. I'd just leave it as is, and then hit the minus button, which will automatically bring in the calculator's best form of that when it types in ANS. That's the previous answer. I want that minus, and then I could type in the square root of 3, which is our last term. We're subtracting there. If I hit enter, it gives me an approximated value of 2.456739397. So again, if you were rounding this, it might have some specific instructions, and if not given, we'll round it to 2 decimal places. So we'll call that 2.46.